Hi, in this video lecture we are going to derive dynamic energy balance equations so that we can solve for both the spatial and the temporal change in temperature for flow going through a heated pipe. So let's first define the problem. So we've got a long pipe, we have flow of some fluid coming in, and it's coming in at a certain inlet temperature, T sub I, and it's got a flow rate of m dot. So as the fluid flows down the pipe, it's going to encounter a constant flux all the way down the length of the pipe. So that flux applied is going to be Q double prime. So suppose there's some sort of electric heating element that's wrapped around the pipe, and that heating element spits out a constant amount of power per unit area, giving us that Q double prime. So our first step is going to be to define a control volume. So specifically, if this is the beginning of our coordinate system, so here is x equals 0, we want to develop an equation to give us t as a function of x and t as a function of time. And I guess we won't necessarily have an equation, but we'll be able to solve an equation numerically, solve this energy balance numerically to give us temperature as a function of x and as a function of time. So our first step, because we want to know the spatial variation of temperature, we're going to define a differential control volume. So we're going to just pick arbitrarily some section of this pipe, and we're going to do an energy balance on that section of pipe. So let's suppose that this section of pipe begins at x, and it goes up until x plus delta x. Let's also define a couple of other nodes here. So we're doing an energy balance on this node. Let's call this node I. That would make this node I minus 1 and this node I plus 1. So we're going to characterize the amount of energy in node I, but we'll see that that's going to depend especially on node I minus 1, because that flow from node I minus 1 at that particular temperature is going to ultimately flow into node I. So our first step is going to be, or our next step rather, is going to be to do an energy balance on node I. So that is going to start by defining our accumulation term. So we're going to have accumulation equals in minus out, and there is going to be no generation in this problem, although there will be this flux, which we're going to treat as an in term. And the reason we treat it as an in term instead of a generation term is because we're doing an energy balance on the fluid itself. So the fluid itself does not generate, it just receives energy from its boundaries. So first, our accumulation term is going to be the fluid's density, and in this problem we're going to assume constant density and constant heat capacity. So it's going to be density rho times our heat capacity Cp times the volume of an individual node. So if we're assuming that this is a circular pipe of radius r, our volume would be pi r squared times delta x, knowing that our node is delta x units thick. So we have density, heat capacity, volume, and then we're going to have dt, so the change in temperature with time, and specifically this is going to apply to an arbitrary node I. So coming into that particular node, we've got our applied flux. So this flux is being applied. There could be an electric heating element that is uniformly applying this energy, which is causing the fluid to heat up both in time and in space. So this flux is going to have units of watts per meter squared, which means to get this in units of watts, or an energy rate, we need to multiply this by the corresponding area over which the flux is being applied. So that area would be the outer surface area of this node. So that's going to be 2 pi r times delta x. Also coming in is going to be the energy that travels into node I from the previous node, which is node I minus 1. So also coming in is going to be our mass flow rate times our heat capacity multiplied by the temperature at node I minus 1. When you're dealing with an enthalpy or heat capacity, so typically this would be a temperature difference, so we could assume that our reference temperature is just 0 and not have to worry about a reference temperature in this case. So similarly, what's leaving our system is going to be, our out term is going to be mCp, and this is going to be the temperature of node I itself. And this is actually the minus out term, so we'll subtract that off. So our energy balance becomes rho Cp times pi r squared times delta x times dt dt. Keep in mind that's specific to node I, is equal to our applied flux and the appropriate area, 2 pi r delta x, plus m dot Cp times Ti minus 1 minus Ti. So if we wanted to solve this numerically using some kind of software, we would want to solve for dt dt explicitly. So we would get dti dt is equal to this whole right-hand side divided by this remaining part of the left-hand side. So we would get q double prime times 2 pi r delta x plus m dot Cp times Ti minus 1 minus Ti divided by this numerator of rho Cp times pi r squared times delta x. So if we wanted to solve this explicitly for dti dt, we would use this equation, and then we would just, to get t at the next time step, we would say that our new temperature, let's use K to represent time, so T at time, actually let me be a little bit more clear, still the ith node, and the kth time step, I'll use a subscript there, is going to be equal to T, still the ith node spatially, and now this K minus 1 is going to represent the previous time step. And let me note that this is going to be an approximation using the Euler integration method, plus dt dt of the ith node evaluated at the k minus 1 times our time step. So by doing this energy balance, we can calculate what our derivative is with respect to time. Once we have that, we can calculate that node's new temperature based on doing this simple Euler integration. I also want to take a step here. I want to go back to this equation. And let's assume that our system is at steady state. So this gets a little simpler. So if our system is at steady state, this whole accumulation term goes to 0. And we end up with an equation that looks like this. 0 is equal to q double prime times 2 pi r delta x plus m dot Cp times Ti minus 1 minus Ti. So here what we can do is we can divide by delta x, divide everything by delta x. So we would get 0 is equal to q double prime times 2 pi r plus m dot Cp, and this term would be, basically this would become a negative delta t, and since we divided it through by delta x, it looks like that. So we can take this equation, and we can take now the limit as delta x goes to 0, and what we get is we get, and I'm going to rearrange here a little bit, we get m dot Cp times dt dx. That came from taking the limit as delta x approaches 0, or as our node itself shrinks to being infinitesimally small. So now we can get this continuous resolution. We have perfect resolution of our system. So that is equal to q double prime times 2 pi r. So if we separate and integrate this system, again, keep in mind that this is at steady state. So up here, we have an equation telling us how our temperature is going to evolve over time, which we can use computer software to solve to give us that T at X and T. Here we're just solving the steady state version, and what we're going to get out of this is just T at X. We're going to get this steady state temperature profile, but we won't know any information about how things evolve with time. So if we separate and integrate here, we get dt is equal to q double prime times 2 pi r multiplied by dx, and that's going to be divided by m dot cp. So we would integrate. So we would get our temperature is equal to q double prime at times 2 pi r over m dot cp multiplied by x plus C1. So how do we get C1? Well, we can apply boundary conditions, and we can say at x equals 0, our temperature is equal to our inlet temperature. So what that tells us is that when x equals 0, T equals Ti. So C1 is equal to our inlet temperature, which tells us that our temperature as a function of x is going to be Ti, plus q double prime times 2 pi r over m dot times cp. So what we're going to do in the next video is we're going to numerically integrate this equation to see how the temperature profile evolves in time, and our hope, if we've done everything correctly, is that our equation will eventually reach the steady state, and I forgot to put an X here, the steady state line, which looks like this. So follow along to the next video. It's going to be provided at the link below, and you can see how we're going to solve this thing dynamically and plot the results in Python or MATLAB.